wonder what lies just beneath the ocean's surface, where the land meets the sea? Good day and welcome to the Continental Shelf, a captivating realm full of life, history, and geological wonders. Today, we are diving deep into this intriguing zone, exploring its unique characteristics, historical significance, and the various types of sediments that define its environment. Together, we will unlock the mysteries of the continental shelf and discover the marvels hidden beneath the waves. But before we dive in, let us take a look at our agenda for today's exploration. So, we will be navigating through 10 subtopics, starting with an introduction to the continental shelf and then journeying through the ancient silicic-clastic shelf sediments. So, as we embark on this exciting journey to explore the continental shelf, we are not alone on this adventure. Just as every great expedition has its team of great explorers, so each member of our team plays a special role in helping us navigate through today's journey. And with that, let us begin.
Hi, I'm Christian Balmes, and before we begin and dig deeper with our main topic, let me first introduce you with our marine environment. So, our marine environment represents the vast portion of the ocean lying beyond the influence of shoreline processes. Further, it is characterized by high diversity and generally large populations of marine life. Our oceans and seas are also known for its saltiness, but more interestingly, although higher or lower salinities can occur locally in restricted bodies of the ocean, the salinity of the seawater in our open ocean averages about 35%. Interesting, isn't it? Moving aside, the water depth in the marine realm ranges from a few meters to more than 10,000 meters. Deep and scary, right? And did you know that our ocean covers 71% of the Earth's surface? Amazing, isn't it? However, as vast and deep as this environment is, it is the least understood, most biologically diverse, and most undervalued of all ecosystems. Now, moving forward, we have here the oceanic realm, which is divided into two major subdivisions, the continental margin and the ocean basin. So, our continental margin is divided into four parts, the continental shelf, the shelf break, the continental slope, and the continental rise, whereas our ocean basin comprises of three parts, the abyssal plains, the mid-ocean ridge, and the deep sea trench. So here, we have a photo showing the parts and the division of our ocean. And from this photo, can you spot the parts that comprise our ocean basin? That's right. These three in the middle are the parts of our ocean basin. This is the trench or the deep sea trench, which is an long, narrow, steep-sided depression in the ocean bottom where the maximum oceanic depths approximately 7,300 to more than 11,000 meters. This one in the middle, that seems like a bump, in the middle of the ocean is the mid-ocean ridge, which are supermountain systems formed by plate tectonics. Oh, and did you know that according to Arthur Holmes and his concept of mantle convection, ridges and trenches are created relative with each other. It is because of the convection currents that pushes the plates together and apart. These convection currents are created by rising and falling heat in the Earth's mantle. Rising heat creates the ridges, and when the heat starts to cool down or when it starts to become a falling heat, the current will pull the plates together with it, and that in turn will become our trench here. Amazing, right? And on the left side of our mid-ocean ridge here, this one here is the abyssal plain, which is basically the flat region on our ocean floor. And that's it. That comprises our ocean basin. Now, can you recite and spot the parts that divided our continental margin? That is correct. The parts here in the sides are the parts that divided our continental margin. Let's start first with our continental shelf here. So basically, A continental shelf is the edge of a continent that lies under the ocean. And even though they are underwater, continental shelves are part of the continent. So the actual boundary of a continent is not its coastline, but the edge of the continental shelf, which brings us with our shelf breaks here and here. So basically, shelf breaks are the submerged offshore edge of a shallow continental shelf where the seafloor transitions to continental slope. And that would be this, the continental slope, which is the seaward border of the continental shelf. Oh, another amazing fact. Did you know that the world's combined continental slope has a total length of approximately 300,000 kilometers and descends at an average angle in excess of 4 degrees from the shelf break at the edge of the continental shelf to the beginning of the ocean basins at depths of 100 to 3,200 meters. Amazing, isn't it? Now, that leaves us with our continental rise here. The continental rise is a low relief zone of accumulated sediments that lies between the continental slope and the abyssal plain. Alright, so that sums up the continental margin. And earlier we mentioned that our ocean realm is divided into two major subdivisions. That is the continental margin and the ocean basin. But that's not all. Our ocean, on the basis of water depths, is also divided into two major zones. That is the neritic zone and the oceanic zone. And here we can see that our oceanic zone consists of the parts starting from the point where our shelf break is located. This one here. So meaning that the shallow neritic zone extends only from the shoreline to the shelf break, whereas the oceanic zone extends from shelf break to shelf break and encompasses the deeper parts of the ocean. So that's it. That covers our marine environment and oceanic realm. And to summarize it up, our ocean is divided into two subdivisions, naming the continental margin and the ocean basin, wherein the continental margin is divided with, that's right, the continental shelf, the shelf break, the continental slope, and the continental rise, whereas our ocean basin is divided with, that is correct, the mid-oceanic ridge, the deep sea trench, and the abyssal plain. And lastly, we have two different zones, and those are right and the money again. The neritic zone, which extends only from the shoreline to the shelf break, and the oceanic zone that extends from shelf break to shelf break and encompasses the deeper parts of the ocean.
Moving forward, let's now explore the concept of the shelf environment. So, it says here, continental shelf environment lies within the neritic zone. So what is the neritic zone? As seen in the image, it is the coastal ocean area that extends from the shoreline out to the shelf break. The continental shelf environment is a vital part of the marine ecosystem. This is because this is the region where most of the ocean's biological productivity occurs, due to the availability of sunlight and nutrients supporting a wide range of marine life. Now, let's break down some of the key concepts. So, the neritic zone, as mentioned earlier, is the shallow part of the ocean. It is the point where the seafloor begins to slope steeply towards the deeper ocean basin. This zone is characterized by its shallow waters, high light penetration, and an abundant nutrients that comes from rivers, coastal runoff, and upwelling currents. This makes it one of the most productive regions of the ocean. And then, since the water column in the neritic zone is relatively warm, it can support ecosystems like coral reefs, kelp forest, and large population of fish, plankton, and other marine species. Now that we know the concept of neritic zone, let's move on to the continental shelf itself. So, it is the submerged and gently sloping extension of a continent. It forms the sea floor within the neritic zone and can extend for hundreds of kilometers depending on its location. It also serves as a transition zone between the land and the deep ocean, collecting sediments from rivers, tides, and waves, which in turn supports the marine ecosystems that can be found there. Next, we have the shelf environment. This is the point where the continental shelf transitions to a much steeper continental slope, as seen in the image. So, on modern continental shelves, the average depth of a shelf break is said to be around 130 meters. But this depth can vary considerably due to different factors, including tectonic activities, historical sea changes, and sediment accumulation, since coastal sediment transport can influence the depth and the structure of the shelf break, so it influences the shelf break. And then, while 130 meters is the global average, the shelf break can be also shallow as 18 meters or as deep as 915 meters. Okay, so let's continue and let's take a moment to further explore the nature of shallow marine environments. So today, these environments that we'll tackle are primarily found along the continental shelf areas surrounding the edges of continents. And presented in your screen is an image. Now, notice and how many environments can you see and figure out? That's right, we have 2. And these are called the pericontinental and epicontinental. Let's first discuss what pericontinental is. So, pericontinental can be found at the right portion of this image, and they are known as marginal seas. This is because they are located around the perimeter of continents occupying the shallow regions of the continental shelf. Examples of these include the North Sea or the Mediterranean Sea, where the landmass and oceans meet, forming highly productive ecosystems that support a wealth of marine life. And then, in contrast, there's another type of shallow sea that existed extensively in the Earth's past. It is called the epicontinental or epiric seas. The key difference between these two types of seas lies in their location and formation. While pericontinental seas form around the edges of continents, epicontinental seas are found within the interior of the continents. So, like shown in this figure, it looks like epicontinental sea is between two land masses. So, these shallow bodies of water once covered vast stretches of land that today are entirely above sea level. So, did you know that throughout geologic history, during periods of high sea levels, these epicontinental seas spread across continental interiors, sometimes spanning thousands of kilometers. They were often only a few meters deep, but they played a major role in shaping the geology and the sedimentary record of those regions. And a modern analogy to this environment can still be found in the Hudson Bay area of the North American Arctic region, which mimics the shallow, broad characteristics of ancient epiric seas. So, let's keep in mind that pericontinental seas are found around continental margins, while epicontinental seas existed within the interior of continents, and marking a stark difference in their location and role within the Earth's geologic history. When we study the modern continental shelf environment, we often use it as a model for understanding the neritic zone. However, it is important to recognize that many shallow marine deposits preserved in the geologic record may have been formed in epicontinental seas, not on modern continental shelves. While some modern continental shelves are quite wide, there are key differences between these environments. So it says here that epicontinental seas received sediments from nearly all sides. This is because they are covered and they are between land masses. And in contrast, continental shelves typically receive sediments from just one side, the landward side, via rivers and coastal processes. Modern continental shelves may not provide perfect analogs for ancient marginal seas due to the rapid sea level rise that followed the last Pleistocene glaciation. This dramatic rise has altered sediment distribution, stranding coarse sediments in deeper parts of the shelf and disrupting the balance between sediment movement and water dynamics. So as mentioned before, a perfect modern analogy for this environment can still be found today in the Hudson Bay area of the North American Arctic region. Now that we've covered the introduction, it's time to introduce our second agenda, physiography and depositional setting. This is where we dive into the physical layout of the continental shelf and how sediments are deposited across different areas. So, before we move on, let me ask, do you know what factors might control where sediments are deposited on a shelf? Is it depth, waves, maybe even ocean currents? Let's find out. So, in the next slide, we'll look at how the siliciclastic shelf environment is divided into three distinct zones: the inner shelf, middle shelf, and outer shelf. Now that we know that siliciclastic shelf is divided into three zones, let's explore them in more detail. So starting with the boundaries, on the landward side, the siliciclastic shelf is connected to various coastal environments. And on the seaward side, it is bounded by the continental slope, which leads down to much deeper waters. Can you guess what's happening in between these boundaries based on the image shown? Well, the shelf environment is divided into the shallow inner shelf, the middle shelf, and the deeper outer shelf. And as shown in the figure, inner shelf can be found nearest of the shore, and then middle shelf follows and outer shelf comes last. The inner shelf, which extends offshore to about 30 meters deep, is shaped by tidal currents, winds, and storm waves. But here's something interesting. Did you know that these boundaries can shift? They're not fixed in place. So when sea levels drop significantly, the inner and middle shelves might even be exposed as dry land. Can you imagine standing where the ocean used to be? And in some cases, the outer shelf could just be below the surface, covered by only shallow waters. Let's explore how the width of continental shelves can vary. So it turns out that this variation is influenced by plate tectonic settings. In four arc regions of convergent margins, where two tectonic plates collide, the continental shelf tends to be narrow. This happens because the intense tectonic activity, including subduction and folding, can compress and uplift the seafloor, limiting the shelf's width. And then, on the other hand, broader shelves often form in back arc basins, divergent margins, and cratonic downwarps. In these settings, tectonic processes create more stable, less active regions where sediments can accumulate over a wider area. Let's dive into the shelf break. So it says here that the barrier forming the shelf break have diverse origins. So these are shown in the image. So firstly, we have basement ridges. So these are submerged mountain ridges that can lift the seafloor, creating a distinct break between the shelf and the slope. Second, we have fold belts. So these are formed by folding the Earth's crust, and these belts can create an even terrain that defines the shelf break. Third, we have fault blocks. So tectonic faults can displace the seafloor, resulting in a step-like transition to deeper waters. Fourth, we have reefs. So coral or other types of reefs can act as barriers, creating a noticeable transition from the shallow shelf to deeper waters. And then next, we have volcanic ridges. So underwater volcanic activity can build ridges that alter the seafloor topography, marking the shelf break. And then lastly, we have diapiers. So these are structures formed by the upward movement of buoyant materials like salt, which can create distinct shelf breaks. So did you know that as time goes by, sediments gradually fill in the depressions behind these shelf margin features? So since they accumulate until they reach the wave base, the depth below which wave-generated processes have minimal effect on sediment movement. So this gradual build-up helps shape the continental shelf's overall structure. Now, let's discuss the equilibrium conditions and surface variations of continental shelves. But before that, let's first define what wave base is. So, wave base is the depth below which wave-generated processes have minimal impact. And once sediments build up to the wave base, the continental shelf reaches a state of near equilibrium. In this balanced state, sediment movement primarily involves bypassing towards the slope. So why is further deposition minimal unless there is additional subsidence or a rise in sea level? When the shelf reaches equilibrium, the sediment supply and removal processes are balanced, meaning further deposition slows down. Additional accumulation only occurs if there is subsidence, which creates more space for sediment as the wave base moves deeper, or if sea levels rise, which shifts the wave base upward and allows sediment to settle in previously shallow areas. And without these changes, the sediment remains stable and isn't actively redistributed. In equilibrium, sediment movement mainly involves bypassing towards the slope. This happens because once sediments reach the wave base, wave forces have little impact on sediment movement on the shelf. Instead, gravity and the gentle slope direct sediment towards the deeper slope, a process known as bypassing. Despite their generally low relief, continental shelves can show significant surface variation. For example, some areas have smooth surfaces formed by sediment accumulation and compaction. Others feature small to large scale bed forms like ripples and dunes, shaped by waves and current action. Near the offshore edge, you might find banks, islands, or shoals, elevated features formed by sediment accumulation that can influence local marine environments.
Hello, I'm Rubenecia, and I will be discussing the shelf sediment transport and deposition. So here, we have 8 bulleted sentences. First, we have wave movement, which is waves move from deep ocean waters to the shore, creating currents and swash. Then, we have sediment movement. Despite shoreward wave movements, sediments can move seaward. Great shelf concept. Johnson in 1919 proposed a decrease in grain size from the shore to the shelf edge. Next, to the palimpsest sediments. Swift, Stanley, and Curry from 1971 found some sediments were reworked during sea level rise, termed palimpsest. Next, we have relic sediments. Research since the 1960s shows purely relic sediments are rare, supporting Johnson's equilibrium shelf idea. Next, ancient shelves. Many ancient shelves may have not experienced significant sea level drops. Then, we have sediment transport. emphasized the need to study sediment transport seaward during high sea levels. So here, waves continuously travel from the open ocean's deepest water across the shelf to the shore zone, where they finally break and transform into longshore currents in wave swash. In response to the assumed decrease in water energy seaward, Johnson from 1919 proposed the concept of a drain shelf, which he believed to display a progressive decrease in grain size from coarse at the shoreline to the very fine at the shelf edge. It was later understood that some relic sediments were likely reworked during sea level rise, aligning them with current shelf process. These sediments, having both ancient and modern trains, were termed palimpsest by Swift, Stanley, and Curry in 1971. Research since the 1960s indicates that Curie relics are rarer than initially believed, supporting Johnson's idea of an equilibrium shelf. Next, we have wave storm dominated shelves, which a variety of transfer processes occur on wave storms dominated shelves, including the four weather waves, storm waves, wind-driven surface currents, radial plumes, and density currents. During calm weather, locally generally wind waves moves from deeper waters to a shallow inner shelf. These waves causes water to move in nearly circular orbits. As a wave passes, water moves forward at the crest, downward under the through, and upward, resulting in water particles tracing an orbital path rather than moving forward with the wave. So here in the first figure, schematic presentation of the major physical process that operate the shelf to transfer sediment. Then on the next figure, behavior of oscillatory waves in shallow water, flattening of orbits as wave enters water shallower than about 1/2 wavelength. Then time velocity record of bottom flow during passage of shallow wave. The landward stroke at the crest passes has higher velocity and moves more sediment than thus return stroke associated with the passage of the throw. So here we have wave base. Orbital motion of water caused by waves diminishes with depth, ceasing of half the wavelength of 10 to 15 meters for fair waves, and wave orbits they are nearly circular in deep water, elliptical in shallower water, almost linear in very shallow water, causing back and forth motion along the seafloor. Orbital velocity varies with waves' orbital diameter and period, strong enough to move sediment grains, resulting in net sediment transfer towards the shore. And breaking waves create currents in shallow water that move sediment onshore and along the shore. The roller energy fence traps sediment near the shore. Then last, sediment escape mechanism includes river mouth bypassing during floods or rip currents. So here, the orbital motion of water caused by waves diminishes with depth, ceasing a depth equal to the half the wavelength known as the wave base. For the fair weather waves, this depth is typically 10 to 15 meters. In deep water, wave orbits are nearly circular, but as waves move into shallower water, the bottom interferes, making the orbits more elliptical. In very shallow water, the orbits become linear, causing a back and forth motion along the seafloor. This motion, called orbital velocity, varies with the wave's orbital diameter and period. When the stronger floors exceeds the threshold for many grains, it results in not sediment transport in one direction. Fair weather waves mainly move sediment on the innermost shelf towards the shore. Additionally, orbital velocity is usually stronger in one direction, which becomes significant when these stronger flows move sediment grains, leading to the net sediment transport in that one direction. Since the fair weather wave base is shallow, sediment movement by these waves occurs mainly on the innermost shelf and is primarily towards the shore. When waves break in a very shallow water, they generate currents that also move sediments onshore along with the longshore current that move laterally along the shore. This shoreward movement of the water above the fair weather wave base creates a lateral energy fence that traps sediment near the shore. Next is about swell, storm waves, and wind force currents. So here we have storm impact. Typhoons and hurricanes generate long-period swells that steer the seabed deeply, affecting sediment transport to the shelf. Beach erosion. Storms erode beach and upper shore faces, pushing sediment seawards via enhanced rip currents and downwelling currents. And wind force currents is influenced by Coriolis force, move deeper water layers and transport sediment to the seabed, and usually flows parallel to the shore but can create coastal setup, leading to the geostrophic currents. Next, combined flows, unidirectionally and oscillatory currents during storm can transport sediment offshore. Seafloor disturbance. Storm waves can disturb the seafloor down to 200 meters, resuspending bottom mud and spreading it across seafloor. Net sediment transport can occur in either direction. So here, swells are long-period waves generated by distant storms, which steer the seabed more deeply than fair weather waves. Storms including typhoon and hurricanes have a significant impact on sediment transport and deposition on the shelf. Energetic storm waves and elevated tides erode the beach and upper shore face, pushing sediment seaward through storm-enhanced rip currents and downwelling currents. Wind force currents created by wind shear stress move deeper water layers, which are deflected by the Coriolis force. This force, caused by Earth's rotation, deflects moving objects to the right northern hemisphere and to the left southern hemisphere. Strong winds can extend water movements to the seabed, transporting sediments. Additionally, geostrophic flows can reach speeds up to 6 cm per second at depths of 10 to 20 meters. These flows alone may not transport much sandy sediments unless combined with strong wave-driven oscillatory motion, which provides a necessary shear stress to the lift grains of the seabed. When unidirectionally and oscillatory currents work together, they are known as combined flows. Tropical storms and hurricanes with strong onshine winds can create higher coastal setups and stronger seaward currents than seasonal storms. These currents can reach velocities up to 2 meters per second on shelves and in submarine canyons. Sediment typically moves obliquely offshore, with some sand shifting from the beach shore face to the offshore areas. However, geostrophic currents usually transport sediment parallel to the isobath, not directly seabed, limiting the distance sediment and move outward onto the shelf. Additionally, storm waves influence sediment movements even deeper water on the middle and outer shelf. Due to their longer wavelengths and period, these waves can disturb the seafloor down to the depth of about 200 meters. The orbital velocities they generate might balance out, preventing net seaward transport. However, these waves can resuspend bottom mud, spreading it across the seafloor. Additionally, net sediment transport can occur in either seaward or landward directions.
So, hello everyone. I am Moiren Lee Areniego and I am here now to discuss about sediment plumes. So, does anyone know what is sediment plumes or hear anything about sediment plumes from before? So, it is the sediment discharge into the ocean from the river mouths and can end up into the continental shelf. So, sediments can be transported as either buoyant or underflows. What do you mean by buoyant? So, what is that? So, first we're gonna discuss the buoyant. Usually, buoyant plumes or hypopycnal flows form in areas with low salinity water. Originating from estuaries and rivers, sits on the seawater with the higher salinity. Usually, these plumes don't extend past the inner or middle shelf before being transported due to the Coriolis force parallel to the coast. So, There, the suspended fine sediment gradually settles to the shelf floor while ocean gets calmer. So the next one is the underflows. So what is underflows? Underflows are also known as hyperpycnal flows, occur near river mouths and bring exceptionally high suspended sediment loads. Means that it is much more saturated with sediment loads, making the river water that is entering the system of the ocean denser than the water of itself. So these flows are in fact the steady flow turbidity currents. So since many of these underflows may be swiftly stopped, the majority of the sediments will be deposited closer or near the river mouths. So the next thing is the nepheloid flow. So again, does anyone ever hear a word or anything about the nepheloid flow? So a nepheloid layer is a turbid body of suspended sediment that may reach the height of several hundred meters above seafloor. So it is also moved seawards as a lateral flow advancing steadily due to its flow density. So in 1965, Ewing and Thorndike used an optical nephelometer to measure the light scattering at different levels of the water column. So this allowed them to subsequently identify and study these stratas, or the flow of the water. So although a nepheloid layer is denser than the ambient water around it, it is not dense enough to sink quickly. Sediments may therefore spend a considerable amount of time suspended in this strata. So the next one is the sediment composition and suspension. The majority of the nepheloid layer consists of tiny clays. Fine particles remain suspended due to their low settling velocity. So sediments can remain suspended in the lowest of 15 meters of the nepheloid layers for the duration ranging from days to weeks and ranging from weeks to months. At the lowest, 1,000 meters of the water column. Resuspension and sedimentation would probably happen often before this technique could transfer fine particles across a shelf entirely. So the next thing to discuss is about the sediment's characteristics of storm-dominated shelves. So first, again, does anyone know what are the storm-dominated shelves? So let me discuss it. So storm-dominated shelves are characterized most of the coast worldwide due to their low tidal current velocities, typically less than 25 cm per second, define them. And the fair weather wave base is normally shallow, more likely 10 meters. And due to these characteristics, except during strong storms, not much coarse materials travel on these shelves. Let me give you some examples of the modern storm-dominated shelves. First is the Atlantic shelf of the eastern coast of United States, and the Pacific shelf of Oregon and Washington, and lastly the Bering Sea. So strong dominated shelves can have a highly complex sedimentation patterns, depending in part on how much current or remnant sediments cover the shelf. So let's go to the sediment transport and pattern. So coarse material transport is minimal except during strong storms. Sedimentation patterns are highly complex and influenced by the presence of current or remnant sediments. And next is the sand bodies and shelf features. So what are sand bodies? So again, let me discuss it. Sand bodies are a distinctive feature of shelves like the Atlantic that have a lot of relic material. The most controversial sand bodies with respect to their origin are shelf sand ridges. Contemporary shelf sand ridges are long, coastal to the shelf sand formation that are larger than subaqueous dunes. They have a height exceeding 20% of the water's depth and length of about 10 kilometers. So these ridges have many similarities and are also seen on shelves that are dominated by tides. But how are these ridges formed? So let us discuss the ridge formation processes. So the incipient ridge grows upwards and migrates down current as a result of interaction between irregularly and storm or tide-driven nearshore or shelf currents. The ridges changes as a result of the ongoing current action or the things that is happening. So the most common time for shelf sand ridges to form is during incursions. Transgressive ravinement or erosion surfaces are thus likely to be overlaid by majority of shelf sand ridges. And let's go to the sediment characteristic and composition. Shelves that includes more modern than relic sediments tend to have less relief and higher percentage of finer grained sediments. So it also includes mads, and relic sands or gravels are visible through the large window in an uneven layer or murky modern sediment, despite the fact that the sediment on these shelves may generally indicate a trend of seaward fining. In certain places, it is also possible for remnant sand and contemporary muds to combine. Usually, these muds undergo extensive bioturbation. The next one is the sedimentary structures in storm-dominated shelves. So this will discuss about the structures and layers of rocks in the storm-dominated shelves. So the first one is the coarse-grained or storm layers, and the second one is the 𝐏𝐿𝐴 cross stratification. So what are the 𝐏𝐿𝐴 cross stratification? It is sedimentary structures that appears to have a special characteristics of storm-dominated shelf sediment. And the next one is the coarse-grained storm layers. It is commonly a thin layer of rocks consisting of concentration of coarser grains interlaid or embedded in finer grained muds. The coarser material is usually composed of gravel, shellfish, and corslets. And sometimes it is also with fine sands. Vertical size grading is generally displayed in these layers. Storm layers are also called tempest tides and are described in considerable detail by Aigner in 1985. And according to Reineck and Singh in 1980, they are best developed on the inner shelf, but they have been found as far as 40 km from the east coast. So how are these storm layers formed? Though their exact origin is debatable, but according to Chill and Leckie in 1992, Storm layers forms in two stages, as you can see in the presentation. We have two stages. The first one is the bed material is transported from a beach by offshore directed or storm generated combined with geostrophic flow. And the second one, or the stage 2, is bed material is reworked and selectively sorted by asymmetrical oscillatory current produced by shoaling swells and waves propagating on the shore. So here in this next slide, here we can see the shallow marine storm bed. And in this figure, it shows here the coarse-grained storm beds and fine-grained 𝐏𝐞𝐲 cross-stratified beds. So the legends is on the bottom side, and in this figure is the schematic comparison of idealized coarse-grained storm beds and fine-grained 𝐏𝐿𝐿 cross-stratified beds on, of course, the storm-dominated shelves.
Hola, I am Joan, Karla's Julianda. Do you like the ocean? I love the ocean too. And in this concept, we are going to talk about the tide-dominated shelves. Do you want to know more about the tide-dominated shelves? Come on, let's do it! But before we start the discussion, let me ask you something. Do you know what a tide is? Is it a laundry detergent? Are you aware of the happenings beneath the countless oceans? Now, we have to dig deeper in understanding the tides, but we don't have anyone to teach us more about it. Who do we call when we need to know more about something? Right, Miss Karla. I need your help to find Miss Karla. Do you see Miss Karla anywhere? Yay! Let us learn all about the tide-dominated shelves. Vámonos! Hola, I am Miss Karla. And now, let me tell you what tide really is. Tide is the regular rise and fall of sea levels around the globe. At times, people in the coastal areas experience this phenomenon and call it low tides and high tides, as they see two of each every day. Factors such as the gravitational pull of the Earth, Sun, and the Moon are the one that affects these tides. The most significant factor is the gravitational pull of the Moon. Even though the Sun is much more massive and has stronger overall gravity than the Moon is still closer to the Earth. So the tide generating force is stronger than the Sun. Also, we know that due to the gravitational pull of the Earth, most things are grounded. But the ocean being fluid, it can be able to flow easily, in which it can be pulled towards the Moon. And this is what creates the tides. Do you know that there are two terms related to these tides? But are you ready to listen more about them? Great! Come on, join me as I unveil these wonderful ideas. In these tides, there's a term called the tidal process, which strongly influences sedimentation in some continental shelves. It can affect sedimentations on tidal flats, in estuaries, and on deltas. On the other hand, tidal current is the vertical rise and fall of tides accompanied by a horizontal movement of those waters. The currents generated on the shelf by tides are bidirectional but asymmetrical with respect to its velocity. That is, number 1, the flood tide, which is a rise in sea level over a period of several hours. And number 2, the ebb tide velocity, which is a stage where sea level keeps receding over several hours. Asymmetrical currents may result in net sediment transport in the direction of a stronger current. If both current phases are able to transport sand, herringbone cross-stratification and reactivation surfaces may also form. In addition, tidal rise and fall in some environments can produce coatlets of sand-mud laminae with pieces of mud deposited on the top of the sand during a standstill. Stacking of these couplets produces tidal successions, referred to as the tidal rhythmites, or what we call as tidalets. Tides are generated by the gravitational attraction of the moon and also the sun for Earth. In conjunction with the rotation of the Earth, it is classified in different types. Well, come on, let's learn more about these types. Number 1, we have the semi-diurnal tides. It is characterized by 2 highs of approximately equal height and 2 lows of approximately equal height as well each day. The interval between the high tides and low tides is around 12 hours and 25 minutes. Semi-diurnal tides are mostly widespread in the Indian Ocean. The other prevalent coast where semi-diurnal tides are experienced are in the Atlantic coast of the United States and the East African coast. So as you can see in the picture, pantay lang yung height and yung level ng waves dito sa ating semi-diurnal. Nakikita din natin na dalawa yung waves ng each low and high tides. So each day, ito ang nararanasan sa dagat ng mga places gaya na lamang ng Atlantic coast sa Amerika and also yung ating East African coast. Now for our second one, we have the diurnal tides. Diurnal tides are distinguished by 1 high and 1 low each day. Owing to the configuration of the generation basin and the complexities of the shoreline. This type of tides refers to a situation when any region experiences only 1 high tide and 1 low tide. The term diurnal indicates a daily cycle which refers to the occurrence of 1 high and 1 low tide on a lunar day cycle. So, the time interval between the high and the low tide is approximately 12 hours and 25 minutes as well. Sa ating semi-diurnal naman, limited lang ito sa 1 high tide and 1 low tide each day. Kasi ito lang yung kanilang i-experience dahil ito sa complexities ng shoreline, pero ando na din yung equal level ng tides na nakikita natin dito sa picture na to. For the third one, we have the mixed tide. This is almost the same as the semi-diurnal tides as 2 high tides and 2 low tides occur in a lunar day cycle. But the difference is that in this case, the heights of both high tides as well as the depth of the 2 low tides are not the same. This means that the 2 high tides have different heights of peaks and a similar difference is observed with the lowest levels of low tide also. Therefore, this tide is called the mixed tide. Sa mixed diurnal naman, sabi nga ay parehas lang siya almost ng semi-diurnal tides na nagaganap as 2 highs and 2 lows. Pero yung pinagkaiba nila ay yung taas ng level ng high tides at yung lalim ng low tides. So kung iisipin natin, madali kang malilito sa ganitong klase ng tides. Pero palagi mo lang tatandaan na yung taas at yung lalim ng each one of them ay pwedeng magkaiba. For our fourth one, we have the spring tide. Spring tide is the alignment of the sun and moon, either it is new or full moon, that are about 20% higher than the normal. A spring tide, popularly known as a king tide, refers to the springing 1/4 of tide during a new and full moon. It occurs twice each lunar month all year long without regards to the season. Sa spring tide naman, kilala siya bilang king tide pero hindi siya affiliated sa spring season. Ito ay dahil ang spring na sinasabi dito ay yung panibagong pagbunga ng new and full moon. So kahit anong season pa to, basta sakop siya sa lunar month, mag-o-occur at mag-o-occur siya. Lastly, we have the neap tides. It is when the sun and moon are at the right angle in relation to the earth, about 20% lower than the normal result. A neap tide, 7 days after spring tide, refers to a period of moderate tides when the sun and moon are at the right angles to each other. This tide occurs during the first and the last quarter of the moon. The gravitational pull of the moon and the resulting oceanic bulge is cancelled out by the gravitational pull of the sun and it's resulting to an oceanic bulge. Also, in contrast to the spring tide, the high tides are lower and the low tides are comparatively higher in neap tides. Ngayon naman, meron tayong neap tides. Dito related yung right angle kasi para siyang yung kabaliktaran lang ng spring tide. Dahil yung spring tide natin ay merong 20% higher than the normal, dito naman ay meron tayong 20% lower. So, nangyayari siya 7 days after spring tide. Tidal currents on continental shelves are propagated as a large wave or a tidal bulge. It is generated in deep ocean basins. However, in major ocean basins, this tidal bulge rotates around a central point of no tidal movement, which we can call as an amphidromic point. Ito yung different classification ng tides na nangyayari sa different parts of our globe. Sa gitna ng mga types na to, we have the amphidromic point. So, ito yung areas wherein walang nagaganap na tidal waves or tidal currents sa ocean. Kung titingnan natin, parang imposible na may part ang ocean na walang current since alam naman natin na magalaw sa ocean. Pero still, we can find this point in different areas na may malawak na katubigan. The tidal wave follows an elliptical path that is almost circular in the open ocean. In more restricted areas, the ellipse is strongly elongated, forming a narrow rectilinear pattern. These points are locations where there is no or little tide in the ocean. This is also related to the influence of the continental land masses interfering with the westward movement of tidal bulges and the influence of the Coriolis effect. Fun fact! There's a lot more to learn about the amphidromic point. Do you still want to hear more? Excellent! Come on! Number 1, we have the closer to the amphidromic point location is, the lower is its tidal range. Number 2, there are about 1 dozen of amphidromic points in the ocean. Number 3, about 5 of these amphidromic points are found in the Pacific Ocean. One of them is near Hawaii. However, there's a little tide changes there, so beaches tend to be narrow. Now that you already know all about the tide-dominated shelves, I'd love for you to hear the next one. Can you sing more for us to continue?
Hola explorers! Today, we're going on an exciting adventure under the sea to explore tide-dominated shelves. These underwater areas are shaped by strong tidal currents that can move super fast, sometimes faster than 150 cm per second. Wow! Our journey will take us to places like the North Sea, Korean Bay, and the waters around Australia. We'll be looking for sand waves, some of which are taller than houses, and some reach the scratch for miles across the ocean floor. And though we don't have cameras on this trip, we rely on reference studies this area in detail. They use advantage tool and technique to reveal these hidden wonders. And we're following in their footsteps to learn all we can about this mystery underwater landscape. So explorers, ready to dive into the world of tides and sun? Imagine the underwater formation waiting for us to discover. Vamonos explorers, together we will uncover the secret of the ocean floor through reference and knowledge. So let's learn about tide-dominated salt. Tide-dominated salt are regions where tidal currents are the dominant force shaping the seafloor, with velocity ranging from 50 to over 150 cm per second. So ang ibig sabihin nito, sa mga lugar na ito, malakas ang alon ng tubig dagat. Ito ang nagdudulot ng pagbabago sa ilalim ng dagat. Ang bilis ng alon mula 50 hanggang 150 cm per second, sobrang lakas kaya naapektuhan nito ang pagkaayos ng buhangin at sediments sa seabed. Another example of tide-dominated shelves includes several globally important areas such as the North Sea, Korean Bay in the Yellow Sea, the Gulf of 𝐿𝐴𝐿 in India, the salt around the British Isles, George Bank in the Gulf of Maine, and the Northern Australian Salt. Sa mga lugar na ito, ang malakas na tidal currents ang pangunahing dahilan kung bakit nagkakaroon ng malaking pagbabago sa mga sediments at buhangin sa ilalim ng tubig. So makikita nyo sa slide na ito yung dalawang larawan. The top image shows a map of the North Sea, a key example of tide-dominated salt, where strong tidal currents have created large sand bodies. Below it, we see a map highlighting the salt surrounding the British Isles, around region heavily influenced by the tidal force. Isn't it fun to learn how tide changed the ocean floor? So first, let's explore the large sun waves or dooms. These are the big sun formation that can range from a few meters to over 20 meters in height with wavelengths for 10 to 100 of meters. So ito yung mga malalaking formation ng buhangin na umaabot mula ilang metro hanggang higit sa 20 meter ang taas at ang haba ay mula 10 hanggang 100 of meters. So they are typically found in large areas covering up to 15,000 square kilometers or more. When the tidal currents are equal during the rise and fall, the dooms are symmetric. However, if the currents are uneven, the dooms become asymmetric. Let's discover the tidal sun ridges. These are long sun formations found in tide-dominated shelves. For example, in the North Sea, these ridges cover areas up to 5,000 square kilometers. They form because of the strong tidal currents that shape the seabed. Lastly, don't forget about other features in tide-dominated shelf. These include sand sheet, sand patches, and gravel sheet. These features have small-scale bedroom and patches of bioturbated mold. They are often in area protected from strong tidal currents and waves. So yung tide-dominated shelf na yan ay karaniwan silang matatagpuan sa mga lugar na protektado mula sa malakas na tidal currents at alon. On tide-dominated shelf, sediments occur very based on tidal current velocity. We can classify this structure into small-scale and larger bed forms. Small-scale bedrooms are the panel sediment features that can be observed and photographed by divers or through remote control camera. These features include ripples and small dooms from the interaction of tidal currents with the seabed. Next is the larger bed forms. On the other hand, are the investigate using more advanced techniques like sonar bottom profiling and side scan sonar technology. Other features include bigger domes, sun ridge, and parallel sun ribbons that may span across vast areas of the seabed. In tide-dominated environment, these bedrooms help scientists understand sediment transport patterns and the dynamics of the underwater landscape. So yun nga, yung small-scale bedrooms ay mas pinong structure ng sediments na maaaring makita at makuha ng litrato ng mga diver or gamit ng mga remote control na camera. Samantala, ang larger scale bedforms ay iniimbestigahan gamit ang mas advanced na teknolohiya tulad ng sonar bottom profiling at side scan sonar.
This diagram illustrates the idealized sequence of bed forms that develop along a sediment transport path on a tide-dominated shelf. Starting for the left side, where tidal velocity are the highest, the seafloor is eroded, creating porous and grabber waves. As the tidal velocity decreases, moving along the path, various bed forms begin to form. These include flow-parallel sand ribbons, large domes, small domes, and rifted sand sheet. At the lowest velocity, farther down the path, we see the formation of sand pitch. In areas with an abundance of sand, sand ridge may also develop within the dome belt. The labels on the side of the diagram indicate the maximum spring tide current velocity associated with each bed form type, demonstrating how this structure changes based on the energy of the tidal flow. Diagram na ito ay nagpapakita ng idealized na pagkakasunod-sunod ng bird forms or mga forma ng sahig ng dagat na nabubuo sa kahabaan ng sediment transform path sa isang tide-dominated shelf. So yun, para sa summary ng ating napag-aralan natin ang tide-dominated shelf and also ang malalakas na tidal currents, 50 up to 150 centimeters. And tinalakay din natin ang malalaking alon ng buhangin o dooms na umabot ng 20 meter ang taas na nabubuo dahil sa tidal currents. And natutunan din natin ang mga symmetric na dooms ay nabubuo kapag pantay ang mga agos habang hindi pantay na agos ay nagdudulot ng asymmetrical na forma. Natutunan din natin ang tungkol sa tidal sand ridge, malawak na formasyon ng buhangin tulad sa North Sea at iba pang tampok tulad ng sand sheet at iba pa. Sa huli, nakita natin kung paano nabuo ang iba't ibang forma ng seabed batay sa bilis ng tidal currents. So, that's all for my part.
Now, we have come to the shelf affected by intruding ocean currents. So here, major surface oceans current flows through the world's oceans like gigantic rivers, driven by the prevailing wind system around the Earth. These prevailing winds, in conjunction with the configuration of the continents and the 𝐿𝐴𝐿𝐼cs forcing arises from Earth's rotation, drive the ocean's currents into gigantic circulating cells, or gyres, that rotate clockwise in the northern hemisphere, which are North Pacific and North Atlantic, and counterclockwise in the southern hemisphere, South Pacific and South Atlantic Indian Ocean. So here we have reworked sediment, which existing sediment is moved and reshaped by currents. Then sand waves up to 17 meter high with wavelengths up to 700 meters. Log deposits, heavy sediment left as finer materials are transported away. Then sand ribbons, long narrow ridges formed by currents. Sediments on such shelves ranked by intruding ocean current is largely relict, but is commonly reworked by intruding currents to the form of sand waves, sand ribbons, and coarse sand and gravel lag deposits. Then we have here that northern western Gulf of Mexico, they are impacted by Gulf Stream system, forming sand waves and reworking sediments. The coast of Southern America affected by the Panama and North Equatorial Current, leading to sediment transport sand waves formation. Taiwan Strait, influenced by the 𝐿𝐴𝐿𝐼𝐿 current, creating extensive sand wave fields, and southern shelf of South Africa, caused by the 𝐿𝐴𝐿𝐼𝐿 current, forming sand waves, sand ribbons, and log deposits. So here, the Gulf Stream system of the southeast coast of the United States, the 𝐿𝐴𝐿𝐼𝐿 current of the Asian coast, and the 𝐿𝐴𝐿 current of the southeast tip of America are examples of some permanent ocean currents. These semi-permanent ocean currents intrude into some shelves with sufficient bottom velocity to transport sandy sediments. About 3% of modern shelves are dominated by these ocean currents, which operate most effectively on the outer shelf, the northwestern Gulf of Mexico, which is affected by the Gulf Stream system, shelves swept by the Panama and North Equatorial Current of the northeast coast of South America, the Taiwan Strait between Taiwan and mainland China, which is influenced by a branch of the 𝐏𝐿𝐴 current flowing from the Philippines. And additionally, the outer shelf of southern Africa, which is crossed by the southward flowing Agulhas current of the western Indian Ocean. These currents commonly contribute little, if any, new sediment to the shelf, but they are capable of transporting significant volumes of fine sediment along the shelf. Some achieve bottom velocity and great enough to transport sandy sediment and create sandways and other bed forms, for example, the 𝐏𝐿𝐴 current and the Agulhas current.
Now, let us discuss the shelf transport by density currents. Density currents are gravity-driven flows that occur within a fluid, such as water, due to the differences in density between two water masses. These currents play an important role in transporting sediments, nutrients, and other materials across the continental shelf and into deeper marine environments. So how are density currents created? So it begins with density differences within the water. And these differences can arise from variations in temperature, salinity, or the amount of suspended sediments in the water. When two water masses with different densities meet, the denser water will sink below the lighter water, initiating the flow of a density current. So let's break this down further. Temperature plays a major role because cold water is denser than warm water, and as a result, when colder water comes into contact with warmer water, it sinks beneath it, generating a density current. Salinity also influences density. Water with a higher salt concentration is denser than fresh water. This is why salty water will sink beneath fresher water. And then finally, suspended sediment content can increase the density of water. When a water mass is rich in suspended particles, such as from the river runoff or coastal erosion, it becomes denser and sinks below clearer water, contributing to the formation of density currents. Let's look at a couple of real-world examples of density currents in action. So in this figure, we can see an example is the buoyant plumes created by estuaries. So estuaries are places where freshwater rivers meet the ocean. So in these regions, fresh water from the river is less saline and therefore less dense than the saltier ocean water. As a result, the river water flows over the denser oceanic water, forming a distinct layer as it spreads out toward the sea. Another type of density flow, as shown in this figure, is the nepheloid flow. So this occurs due to the high concentration of suspended sediment within the water, making the water denser than the surrounding water, but not dense enough to sink rapidly to the seafloor. So instead, the nepheloid layer moves slowly along the ocean bed, often being transported laterally across the shelf. Heat plays a crucial role in shaping ocean currents. In particularly hot, arid, or desert climates, excessive heat leads to nearshore evaporation. This process intensifies salinity, creating dense brines. So these brines are saltier and denser than standard seawater, which causes them to sink beneath the less dense, warmer surface waters. Once these dense brines form, they move seaward along the bottom in what's called an underflow. So this process can also happen on continental shelves where cold surface waters sink and move seaward. However, while density currents generated by variations in temperature or salinity do occur, they are not the main agents of sediment transport on modern shelves, and no modern shelf is dominated by such processes.
So, what is happening? So, during this fluctuation or changes of sea level, various erosional and depositional processes are influenced. It directly affects the types of sediments that eventually settle and lands at the bottom of the shelves. The alteration in these sea levels play a role, or it plays a big role in shaping the stratigraphic architecture of shelf sediments. So, when the sea level rises, it causes sediments to be transported farther offshore and depositing finer sediments. And the falling sea level lead to erosion of exposed shelves and transport of coarser sediments closer and more near to the shore.
Hola amigos! Today, we're going to learn about the amazing activities happening on the continental shelves. Do you know what a continental shelf is? It's the underwater area along the edge of the continents, and it's not as deep as the open ocean. These shelves are really important because they home to a lot of marine life. They provide habitats for many organisms and are rich in nutrients, making them essential to marine ecosystem. Also, did you know that the organism living in the sediment help mix things up? This is called bioturbation. Bioturbation is when small organisms dig or move through the sediment, mixing it around. Why is it important? Well, the activities help circulate nutrition and oxygen through the sediments, keeping the ecosystem healthy. Plus, they move and leave traces in the sedimentary record and learn about past environments. So, let's go explore how they do it. Modern continental shelves are full of different kinds of invertebrates. We have mollusks like snails and clams, which either move on top of the sediments or burrow into it for protection. Maintindihan natin, ang modern continental shelf daw ay tahanan ng napakaraming uri ng invertebrates o mga hayop na walang buto sa loob. Ilan sa mga kilalang invertebrates na makikita dito ay ang mga mollusks tulad ng mga suso at tulia. Ang mga ito ay maaaring gumalaw sa ibabaw ng sediment o kaya ay makay at magkubli sa ilalim nito bilang proteksyon mula sa mga predator. Dahil dito, nagiging ligtas sila mula sa mga mabibilis na alon o mga mandaragat na nasa ibabaw ng tubig. Echinoderms such as sea star and sea urchin have spiny bodies and move slowly along the surface. Mga echinoderms naman tulad ng mga sea star at sea urchin ay may mga matitinik at matitigas na katawan. Mabagal silang gumalaw sa ibabaw ng sea floor, naghahanap ng pagkain tulad ng mga maliit na organismo or mga patay na material. Hindi lamang sila pangkaraniwang makikita sa mga tide-dominated shelf, kundi malaga rin ang kanilang papel sa marine ecosystem. Sila ay tumutulong sa pagpapanatili ng kalinisan at balanse sa pagkain. Corals build coral reefs that provide homes for other sea creatures. So, meron din naman mga corals na bumubuo ng mga coral reefs. Ang mga reefs na ito ay parang mga lunsod sa ilalim ng dagat, nagiging tirahan ng iba't ibang uri ng mga hayop dagat mula sa maliit na isda hanggang sa malalaking invertebrates. Sa mga reefs na ito, nabubuo ang mga tahanan para sa nilalang na mangangailangan ng proteksyon at ng pagkukuhanan ng pagkain. While spongi filter the water, cleaning as they fill. Ang mga sponges naman ay nagsisimbing natural na filter ng tubig habang kumakain sila ng mga maliliit na particles sa tubig. Nalilinis nila ito kaya't nagiging mas malinis at mas maayos ang kapaligiran ng dagat. Some invertebrates live inside the sediment, which is the impuana, burrowing deep for protection in food, while others live on top, impuana, moving around and hunting for food. Most of these animals prefer the quiet, lower energy parts of the inner shell because it's calm and stable, just like a peaceful neighborhood. Meron din mga invertebrates na nakatira sa loob ng sediments. Tinatawag na impuana, karaniwan sila naguhukay ng malalim upang makahanap ng pagkain at proteksyon mula sa alon o predator. Samantala, ang mga impuana naman ay nakatira sa ibabaw ng sediment, kung saan sila ay malayo nakagalaw at nakapangaso ng kanilang pagkain. Yan sa mga invertebrates na ito ay mas gustong manirahan sa mga lugar na mas may bababang enerhiya o mas tahimik na bahagi ng inner self. Dahil ang mga lugar na ito ay kalmado at matatag, para bang isang mapayapang komunidad. Dito, mas madali nilang makukuha ang kanilang pangangailangan ng walang labis na panganib mula sa mga malakas na alon o iba pang panganib sa mas magulong bahagi ng dagat. So for a brief summary of this page, the continental shelf is home to diverse sea creatures. Mollusks moves on the surface or burrow in the sediments, while sea star and sea urchin move slowly. Coral-built reefs and spongia help clean the water. Some animals live in the sediment and others stay on top. The calm, the stable condition make the inner self an ideal environment of this species. So let's move on to this page. In this page, we're gonna talk about bioturbation and sedimentary characteristic. Inertia high energy zone, it's hard for many organisms to survive. The waves and currents move the sun around too much, making it difficult for animals to burrow or stay in one place. Instead of seeing bioturbation, we mostly see physical sedimentary structure like cross bedding. These are layers of the sun that has been pushed around by the water, forming different shape, but in these raw areas, we can something find traces of bioturbation, like escape burrows, vertical tunnels that animals dig when they need to get away from the shipping sun. In deeper water, when it's much calmer, organisms burrow in oblique or horizontal direction. In this area, sandy sediments may show bioturbation, mostly in the upper parts, while modest sediments are highly bioturbated, sometimes even erasing other physical sedimentary structure. Wow, isn't it amazing? In summary, nearshore high energy zones are challenging for many animals due to shipping sun caused by waves and current. Instead of animal diggings, we mostly see sun layers shaped by water. We find escape burrows where animals have to dig to avoid moving sand. In deeper calmer waters, animals can dig in different directions, and we see more evidence of their burrows. These show how organisms adapt to their environments. For summary, organisms contribute to sediment formation in many ways. Some produce fecal pellets that harden and behave like sand grains, while others leave behind shell fragments that can be preserved and become part of the sedimentary record. We explore the amazing continental shelves and learn how important they are for marine life. We saw how organisms mix sediment with bioturbation, keeping the ecosystem healthy. We also discover how invertebrates live both on and in the sediment, and how even in thaw areas, they leave behind clues of their activities. And we learn that these creatures also help from sediment. Great job exploring with me today. See you next time for more adventures.
So now, we're gonna discuss about the ancient siliciclastic shelf sediments. So what is that? So siliciclastic, or commonly referred as clastic, are rocks that are composed of terrigenous material formed by weathering of pre-existing rocks or already formed rocks that experience weathering. Next, so although recognition of ancient shelf sediments is aided by study of modern continental shelves, modern shelves are not necessarily a good analogs of ancient shelves. For example, the prevalence of relic sediments on modern shelves may be a typical one, and conversely, some structures believed to be a diagnostic of ancient shelves sediments, notably storm-generated 𝐏𝐿𝐴 cross stratification. It has apparently not been recognized in modern shelf environments.
Now, let us discuss the characteristics of an ancient shelf sediment. Number 1, it has a tabular shape. Number 2, it has an extensive lateral dimensions of thousands of square kilometers and great thickness of about hundreds of meters. Number 3, it has a moderate compositional maturity of sands with quartz dominating feldspars and rock fragments. And then, it is generally well developed, even laterally extensive bedding. It has storm beds in some of its shelf deposits. It has a wide diversity of abundance of normal marine fossil organisms. And lastly, it has a diagnostic association of trace fossils.
Thank you for that. And hi, I'm back again. But other than that, we also have a more specific characteristics that are related to deposition under tide-dominated or storm-dominated conditions. So for ancient tide-dominated shelf, first is that its deposits are characterized by crust-bedded sandstone. Now, when we say crust-bedded, it is a sedimentary feature characterized by layers that intersect with each other. And for our ancient tide shelf here, it can be characterized when its deposits of sandstones are intersecting with one another. Moving forward, its paleocurrents are mainly unimodal, apparently because of ancient regional net sediment transport spot, although bipolar cross-stratification is present locally. So, when we say paleocurrent, it is a sedimentological feature contained in all sedimentary deposits which enables the direction of movement of the sediment and the containing fluid at the time of deposition to be determined. Now, when we say unimodal, it means one primary direction, meaning that in our ancient tide-dominated shelves, their sediments are moving all in one direction. And lastly, in ancient tide-dominated shelf, reactivation surfaces are abundant. When we say reactivation surface, it is a discontinuity cutting across a forested, generated by erosion or changing flow strength before the resumption of the forward migration of the forested. Next up is the ancient tide-dominated shelf, which deposits are likely to contain a greater proportion of mud. Following that feature is that humpy cross stratification and storm layer are common, yet in our modern dominated shelf, these are not that commonly seen. So those are the distinguishing features of ancient shelf sediments relative to whether the deposition takes place under tide-dominated or storm-dominated. Now, several kinds of vertical successions may thus be generated in shelf sediments, depending upon whether deposition takes place during transgression or regression and depending upon the dominant type of shelf processes operating during deposition. So generally, it is difficult to generalize about these successions, except to say that transgression tends to produce spinning upward successions that may begin with coarse slag deposits, and regression produces coarsening upward successions. So here we have an idealized diagram illustrating the typical pining upward transgressive shelf succession on a tide-dominated shelf and a storm-dominated shelf, and a coarsening upward regressive shelf succession on a storm-dominated shelf. Now, from this photo, can you spot the transgressive and the regressive shelf? That's right. Figures A and B are the transgressive, wherein A is the dominated shelf and B is the storm-dominated shelf. That leaves us with C being the regressive. Now, can you spot and tell the difference of transgressive and regressive with this figure? Awesome, that's correct. Transgressive, whether it is tide-dominated or storm-dominated, produces spinning upward succession that starts with coarse slag gravel and sand, as you can see here, and ends with fine-grained mads like these bioturbated silts and mads on our transgressive tide-dominated shelf in Figure A, and the laminated carbonaceous mads and borrowed glauconitic silty mads in the transgressive storm-dominated shelf in Figure B. On the other hand, regressive shelves, as you can see here, produce coarsening upward succession that begins with fine-grained mads and ends with coarse-grained sands. Oh, and that's right. Here in our tide-dominated shelf, we can see a reactivation surface like we have mentioned earlier as one of its distinctive characteristics. This one here, And both of our storm-dominated shelves here, both transgressive and regressive, have hummocky cross-stratified feature. This one here in the not-so-bottom layer in figure B, and this one here in figure C. So, that's it. The main difference of our shelves under the influence of transgression and regression is that transgressive, whether it is tide-dominated or storm-dominated, produces fining upward succession that begins with coarse sand deposits and ends with fine mud deposits, whereas regressive produces coarsening upward that begins with fine mud deposits and ends with coarse sand deposits. But remember, these successions should be considered only as working models. Actual transgressive and regressive successions may differ markedly in detail from these idealized profiles. Next up here is a photo showing an example of shelf deposits from the Western Interior Seaway, wherein on 1991, Banerjee describes Cretaceous sandstone of southern Alberta, Canada, which he interprets as tidal sand sheet bases. One of these is the lowermost Sankey member of the Lower Cretaceous Alberta group, and that is what is shown in this figure. So this sandstone unit, that is approximately 10 meters thick, rests with a sharp erosional base on non-marine shales on the Beaver Mines Formation and is overlain by black marine shales. Now, can you spot the Beaver Mines Formation? That's right. This is the Beaver Mines Formation, where the sandstone unit rests with, and it also has that erosional sharp base like Banerjee describes. The Sankey member consists mainly of sandstone, with a thin lag gravel deposit at the base and a few thin interbedded conglomerate layers interpreted as storm layers. So further, this succession as a whole pinds upward. Also, the basal sandstone units are cross-bedded. The uppermost one are characterized by placer and wavy bedding. So, from this photo, can you spot the layer number of the cross-bedded layers and the placer and wavy bedding layers? That's right. Layers from 1 to 3 are cross-bedded layers, whereas the upper layers starting from 4 until 10 are characterized by placer and wavy bedding. So, foraminifers and dinoflagellates are also present in some layers, and bioturbation is not that common. So, can you spot what layer the foraminifers and dinoflagellates are present? That is awesome. The foraminifers are present in our layer 1 here, and the dinoflagellates are present in the layer 8 here. So, as mentioned earlier, Banerjee interprets these sandstones as tidal sandsheets. Tidal interpretation is based in part on the presence of the following: cross-stratification, where it should be greater than 20 degrees deep and sets 30 to 40 centimeter thick. And we can see that here in our layers 1 to 3. It should also have the presence of thin shale drapes adhering to porous set surfaces, and in the lower part of the section, that is our layer 11 here and this base here. And lastly, the presence of placer, wavy, and lenticular bedding in the upper part, like our layers 4 to 10 here. And again, lastly, the transgression deepened the water at this site, causing black marine shales to be deposited on top of the tidal sandstone. Thus, our layer 11 here. And that's it. That is the example of a vertical succession of sandy tidal shelf deposits found in the Sankey Sandstone member of the Lower Cretaceous Alberta group, Southern Alberta in Canada. Thank you for listening. I hope you learned more, and see you again in our next exploration.
Yay! Let's go! Now that you reach your final destination, this would end our discussion all about the continental shelf environment. I do hope that you have learned something new and joining our exploration. together with my co-presenters Janelle Rae Cruzat, Rubenecia, Moiren Lee Areniego, Balmes, Sheanne Pañoso, and yours truly, Joan, Karla, Julianda. We thank you for lending your eyes, ears, and opening your mind to the stratigraphical concept. We did it! Of course, we are the group Continental. See you again in our next topic. Bye!